Because the dynamics exam was hard, I'll make this one easy. Okay, exam 2 is Friday. And I think I said the topics are just going to be up through stresses due to bending moment. Okay, any questions about the test? So this problem, as it's written, is a bad example of something that could be on the test. But if we modify it a little, it can be a good example. So let's modify it a little. Okay, if you just did it like this, that torque would make it rotate around the pin. So there would be angular acceleration, and so that doesn't work. So this isn't statically indeterminate. This is a rigid body dynamics problem that could have been on the dynamics test.
Is that where this came from?
No. So it's actually not statically indeterminate, although, I mean, that's the right way to think of it. It's really
Not static.
going to accelerate.
Drawing is useful.
Yeah. So, okay, let's change it. Okay, so let's say instead we have a fixed joint and a 2,000 Newton meter couple there and a force of 4,000 newtons here. And we want to calculate the greatest absolute value of normal stress. Okay, so this is one where we're going to have normal stresses in the x direction due to tension compression, and we're going to have normal stresses in the x direction due to the bending moment. And on one half of the beam, those are going to sort of offset each other, and on the other half, they're going to add. And so the biggest absolute value of normal stress is going to be on the side of the cross section where they add instead of cancel, you know. And that's kind of the idea if you ever hear about pre-stressing. You can imagine if you're very concerned about, so like, say that without this 4,000 Newton force here, there's going to be a part on this beam that you're afraid of, where you're afraid of the beam fracturing. You can apply this pre-stress to it that's going to partially counteract that stress, you know? And so even though you're adding more external forces to it, the effect is going to be to reduce stresses at some important location, you know? All right, so we got to start with calculating the external loads. So we have a reaction force and a reaction couple, I'll call MR. We have a 4,000 Newton force here, and then a couple of 2,000 Newton meters here. That's a really big couple. Newton's second law says Rx, Ry plus negative 4,000, 0 is equal to zeros. So R is equal to positive 4,000, 0. And then the moment equation, we have MR plus 2,000 is equal to 0. So MR is equal to negative 2,000 Newton meters. And now we can do our cuts. So cut 1, the length of this is 2 meters. So cut 1 is going to be for the left half, for x's between 0 and 1. And we have a reaction couple here of 2,000 that way, and a reaction force of 4,000 newtons, and then T, V, and M. Newton's second law says 4,000, 0, plus T negative V is zeros. And so T is equal to negative 4,000 and V is equal to 0. And the moment equation about the z-axis, we don't have any torques in this. So about the z-axis, we have negative 2,000 plus m is equal to 0. I guess you could say we also have minus v times x, you know, like always, but that goes away because v is 0. So m is equal to 2,000 Newton meters. And then cut 2. This is for x's from 1 to 2. So here we have still the 4,000 and the 2,000. But this time we have the 4,000 going this way. And then the internal loads. So Newton's second law says 4,000, 0, plus T negative V I missed the one in the middle. Negative 4,000, 0, plus T negative V is equal to zeros. So T is 0, V is 0. And then the moment equation about the z-axis says negative 2,000 plus m minus vx is equal to 0. Vx is 0. So m is equal to 2,000. Okay, so we are going to get an x normal stress. So every cross section is going to have the same profile of x normal stresses, okay, because the bending moment is the same over the whole beam. And so the biggest absolute value of stress, since that's not going to change as you move along x, the biggest absolute value of normal stress is going to be when you have a normal stress due to tension compression, because then they can add to each other. Okay, so the biggest absolute value of normal stress is going to be in cut 1. Okay, so let's think about cut 1. And first we're going to do the stress due to tension compression. Sigma xx is equal to T over A. T is negative 4,000. A, we're given the cross section, so it's 0.05 for a height of the cross section, 0.02 for the width. And the neutral axis is, it goes through the centroid. So there's the neutral axis. So 4,000 divided by 0.05 times 0.02.
That's 5,000,000. 4 times 10 to 6.
Okay, thank you. 4 times 10 to the 6 pascals. And so the stress tensor due to tension compression is negative 4, I'll write it in megapascals. Okay, now, this beam has couples on it like this on the right and like this on the left, we figured out. So this is like curving it into like a smile, you know? And so which side, if it's being bent into a smile, is the top or the bottom of the cross section going to be in compression? Top is going to be in compression, bottom is going to be in tension. And so where do we expect the biggest absolute value of normal stress? Top, because we're in compression due to tension compression.
Because they cancel each other out.
So on the bottom, they'll at least partially cancel each other out. It's unlikely it's exact, you know, but they're going to be going in opposite directions. Okay, so let's think of, anyways, the top and the bottom as sort of the two candidates, and we'll do it for both. Okay, so now we're going to do the stress due to the bending moment. And the formula says sigma x is equal to negative m times y over I. And I'm going to do the top and the bottom both, and we'll see how it works. So I guess before the moment of inertia, the area moment of inertia is the same for the whole cross section. That's not done point by point. Okay, so I might as well calculate that first. So our I is going to be equal to 1/12 times the base, which is 0.02, times the height cubed, so 0.05 cubed. So that is 2.08, then 3's repeating, times 10 to the minus 7 meters to the fourth. So now we'll start with the top. Sigma xx is equal to, the bending moment is positive 2,000. What's y at the top of the cross section?
0.025.
Right, the height is 0.05. The neutral axis goes through the centroid, so y is half of that. And then we're dividing by 2.083 repeating times 10 to the minus 7. This is going to be just an absolutely ginormous stress that is going to rip this thing to shreds, I think.
Shreds, you say.
Yeah, 2.4 times 10 to the 8. And it's negative. And so the stress tensor due to bending is negative 240, zeros everywhere else. And this is in megapascals. And so the total stress tensor at the top is negative 400 plus negative 240 and so we get negative 244, zeros everywhere else, and this is in megapascals.
Is there anything that would be able to withstand that?
Well, I do not think so. I really don't know what I don't know what diagrams look like for. So, like, if you look at the tensile test, like stress versus strain curve.
So that's a compression, right?
That's compression. And so that is compression. One thing that you would have to worry about here in this particular configuration is that this would probably buckle even before it failed in pure compression. So that makes the problem even worse, you know. I think the answer is nothing could withstand that.
This is AI, but
Yeah.
It says that concrete compressive strength in megapascals typically ranges from 20 to 34.5.
Yeah, right, right. And this is a beam, not, you know. So I think the answer is no. Okay, but let's think about the bottom now. So this worked out the way that we figured out it was going to work. You have compressive stresses at the top because of the way the couples work, and you have compressive stress due to compression. And so those add and you get this. At the bottom, I mean, what's the answer going to be before we do the calculations?
236.
236, exactly. I mean, it's going to be, because of the symmetry of that rectangular cross section, we're going to get the exact opposite XX normal stress due to bending, and it's going to be added to a -4, so we're just going to get positive 236. So at the bottom of the cross section, we know that our stress tensor due to tension compression is -4. And then the XX due to bending is -my/I. Our M is 2000. The thing that switches the sign is the Y is negative now, so -0.025. We're still dividing by the same area moment of inertia. 2.083 repeating times 10 to the -7. And so we get positive 240. And so the total stress tensor at the bottom is positive 236. MPa. Any questions about that? Any other homework questions you want to see? All right, well, let's do an example with a shear force. So remember that what we learned last time is when you have a shear force, it's an XY shear stress that's developed, and it's equal to negative shear force times Q, which is that weird area calculation, divided by the area moment of inertia times the width of the beam at the cross section that you care about, at the sort of at the height of the cross section that you care about. And what are the beam requirements for shear stresses? It's a good habit to get into to always ask yourself this before you do these questions.
Must be either rectangular or circular.
Wow, you remember that just straight off the top of your head? Good job. Yes, and there's more. Remember?
Height greater than base for rectangular.
For rectangular, so it can be rectangular, but it needs to be taller than wide to be accurate. The taller it is compared to the width, the more accurate it is, because it's just making assumptions that let you cancel out some terms. And then the second one is, okay, it can be circular, but in that case, we can only calculate the stress along the neutral axis, nowhere else on the cross section.
Oh, but in the rectangular one, you can do it.
You can do it everywhere. That's right. Okay, so and what's the meaning of Q? So if this is the neutral axis, and this is the line of interest, Then find the centroid above the line of interest or below. Calculate the area above the line of interest. Calculate the distance from the neutral axis to that centroid. And Q is equal to the area, that blue area times that distance. Okay? That means absolutely nothing physically. That's just when you go through this long derivation, you end up with a bunch of factors that you go like, oh, at the end, like I can group these together and call it one thing to sort of simplify how to memorize this. So that's the way that that works. All right, so now let's say that the problem we're going to do we have a cantilever beam. And the beam is 2 meters long. And we want to calculate the stress at the middle of the beam. So this is the desired location. And then on the cross section, we have a height of 10 centimeters, 0.1 meters, and the width of 2 centimeters. And the neutral axis goes through the centroid, and we want to calculate the stress at this line that's a midpoint between the top and the neutral axis. So we want the stress along this line. We can skip calculating the external loads for this one because the only external load we don't know is at the extreme right end, and that never comes up in cuts. Okay, so let's go. What external loads are there? I didn't give you a mass, but clearly I have to. So the mass is equal to 100 kilograms, and we're just going to calculate the stress due to that weight. Okay. So the first cut, this works for all the, and really we could just do it for, I mean, we're just trying to find it at a location, but I might as well do a full mathematical cut. Why not? So this is for x's between 0 and 2. That weight is 981 newtons, but it's spread out over 2 meters. So we have a distributed load that's equal to 981 divided by 2. And so this is 490.5 newtons per meter. And then we have our internal loads, tension, shear force, and bending moment. Okay. Now to do the calculation, we have to treat that distributed load as a point force. The centroid of that distributed load is the middle. The length is x, the height is 490.5, And so the magnitude of the point force is 490.5 x. And so we have this force down from the weight that's equal to 490.5 x. And then we have the internal loads. Newton's second law says 0, negative 490.5 x plus t negative v is equal to zeros. So t is 0. V is negative 490.5 x. The moment equation about the z-axis says m minus vx is equal to 0. So m is equal to negative 490.5 x squared.
Are you sure?
No, I am not sure.
Because the moment arm is half.
Is half, yes.
No, you need 2 seconds.
Oh, because I didn't do the weight. Okay, thank you.
It gets confusing because V is only the weight.
Yeah. So go back up to the free body diagram. This is a negative moment of x over 2 times 490.5 x. And then minus Vx is equal to 0. So m is equal to positive 245.25 x squared minus 490.5 x squared. And so m is negative 245.25 x squared. That's more like it. So now the derivative relationships work. dm dx is equal to v. dv dx is equal to that constant distributed load. And so now at x equals 1, that's the only place that we're calculating this stress, so we can plug that stuff in. We get that t is 0, v is negative 490.5 x, and m is negative 245.25. And now that we have those internal loads, we can start calculating the stresses. Tension compression, this is equal to T over A, which is 0. So there's no stress due to tension compression. Now bending moment, sigma xx is equal to negative my over I. Can we do the calculation for, like, can we trust? Of course we can do it. You can calculate anything, you know. But can we trust our calculations for the stress due to the bending moment? Like, think about the beam requirements for bending moment. It has to be straight. It has to be prismatic, so the cross-section doesn't change. And it has to be symmetric about the y-axis. So we're good for bending moment. The I value is 1/12 times the base times the height cubed. And I get 1.6 repeating meters to the fourth. Our Y value, if we look at the cross section, what's the Y value at that blue line? So if you go from the neutral axis all the way to the top, that's 0.05. That's half of the height. We're going half of that distance, so it's 0.025. And it's positive because we're above. And so sigma xx is equal to negative of negative 245.25 times 0.025 divided by 1.6 repeating.
That should be times 10 to the negative 6, or 1.6.
Oh, really? What's
Yeah.
that?
Well, you have 0.1 cubed.
Yes.
Mm-hmm.
0.02 times 0.1 cubed. Yes. Okay. I thought that seemed so big. 1.6 repeating times 10 to the minus 6.
Yeah, that's the difference between pascals and megapascals.
Yeah, right. 1.6 repeating times 10 to the minus 6.
So close, just a factor of a million.
Yeah. Times 0.0.
I call that close enough.
Mm-hmm. It's like astronomer close.
And so we get 3.68 times 10 to the 6 pascals. That's pretty amazing. That's a big stress. And so the stress tensor due to the bending moment is 3.68, zeros everywhere else, in megapascals. And now we're going to do the one for the shear force. So we have to calculate the Q. So Q is equal to the area times the distance. What's the area above that blue line? Well, it's 0.025 is the height of the rectangle above that blue line, times the width, 0.02. So that's 5 times 10 to the minus 4. And now that distance is the distance from the neutral axis to the centroid of the stuff above here. So it's from the red line to this. Okay, so that is 0.025 to get from the neutral axis to the blue line. Then another 0.0125 to get from the blue line to the centroid of that shape. So 0.0375. Any questions about that? And so Q is 1.875 times 10 to the minus 5.
Wait, how did we get that E again?
Here's the cross section. The whole thing, well, I'll just do so here's the neutral axis. And from the neutral axis to the top is 0.05. Okay. So from the neutral axis to the midpoint there is 0.025. And then the distance is to the centroid of all the stuff above. And so this last distance is half of that height, so 0.0125.
So that first line you drew that's at the top quarter, that's never mind.
Anybody have any questions about that? Are you with me on that? So it's because it's not going to the line of interest, it's going to the centroid of the area above the line of interest. Okay, so we got Q. We already have I, so we can calculate this stress as negative. Shear force is negative 490.5. Q is 1.875 times 10 to the minus 5. I is the area moment of inertia, 1.6 repeating times 10 to the minus 6. This thing has the same base width everywhere along the cross section, so the answer is just going to be 0.02. That's our B. And I get positive 0.276 times 10 to the 6 pascals. So the stress tensor due to shear force is 0, 0.276, 0. Then symmetry requires that this one is 0.276, 0, 0, and zeros. And this is all in megapascals. And so now we can put these together. The total stress tensor is the stress tensor due to tension compression plus the stress tensor due to bending moment plus the stress tensor due to shear force plus the stress tensor due to internal torque. This one and this one are 0. And so we get 3.68, 0.276, 0, 0.276, 0, 0, and this is in megapascals. Anyone have a estimate of the principal stresses for this? We're really close to being a principal stress tensor.
4?
And so, yeah, I mean, it's going to be probably 3.68, really. It's definitely going to be 3.7 if you're willing to be that imprecise, you know? Any questions about that? Okay, that's all.